We will now continue our study of the atoms, which will lead us into beginning the understanding of the periodic table of the elements, section 4A, organizing the elements. Here we go. And there you see a modern periodic table of the elements. Realize, though, that we didn't always have a nice, neat chart to look at. And obviously it took many, many years, decades, even a few centuries for all the elements to get discovered. So imagine trying to build the periodic table over all these times. You'll find that as you study this in more depth, that some of the elements weren't yet discovered, so how did scientists know where to place them on the chart? The next set of notes will talk even more about that. This time it's just more of a history about some of the scientists who helped form the periodic table over those many years. Let's begin. Diamond and anvil cells. Now keep in mind, diamond is made of one particular element, carbon. So is charcoal, and actually so is the pencil lead that you might be writing with. That pencil lead is not lead, that's a form of carbon we call graphite. But we have many different types of carbon, or at least enough that we can talk about the differences here. Diamonds and charcoal are both made of carbon. Well, charcoal is fairly soft, very flammable, and conductive of heat. But diamonds, they're the hardest known substance, but they're both made of the same element. Well, look at the picture, and you see the force going down, the force going up, putting tremendous pressure on that sample of carbon that's going to become a diamond. Carbon has a high thermal conductivity, which simply means thermal meaning heat, conductivity meaning how well the heat travels through carbon. Well, where else do we find carbon? Charcoal, of course, that burns on the grill and helps cook the steak or the hot dogs or the burgers or whatever else we want to cook. Carbon is very conductive of heat. Now these diamond anvil cells, they're tiny laboratories, and that's where scientists help generate that extreme pressure and the temperatures required to make diamonds. Now some diamonds have occurred naturally, but carbon can be forced into diamond in these little laboratories called anvil cells. And the picture again shows just a very, very brief rendition of how that might happen. A high force coming from above, a high force coming from below, X-ray beams shining through and getting that sample of carbon. Very, very highly pressurized, very, very hot to get that carbon to form into diamonds. Of course, it's a whole lot more complicated than that. Ready? Oh, forgot that last line. Testing helps to see if living cells can survive similar conditions. But doing the testing on the non-living materials, well, that's what we want to do, and then we can see if living cells are able to survive those conditions. Now, ready. Why do we need a periodic table in the first place? Well, remember, we have about 118, actually exactly 118 known elements. It would be very difficult to keep track of all the information if we did not have a very well organized chart to look at and study. 118 known elements, half of those were discovered in the last 160 years. That may seem like a long time, but considering that it took many more years to discover the first half of those, well then that's actually fairly quick in comparison. 7 of the elements are mentioned in the Bible: gold, silver, lead, copper, tin, iron, and sulfur, although the Bible may call sulfur brimstone, and that may depend on which version you're looking at. King James Version, remember, fire and brimstone. And the letters in parentheses that you see there, those are the chemical symbols of each element. Gold, AU, silver, AG, lead, PB, and so on. And as we said last time, each element has its own atomic number. Gold is 79, silver is 47, lead is 82, copper is 29, tin is 50, iron is 26, and sulfur is 16. Remember, atomic number means the number of protons in the atom's nucleus. Alchemists are people who studied the elements, and again, it took many, many years, decades, and a few centuries to get all the information that we know about the elements. Soon, however, there were just too many to keep track of without some type of written organization. So scientists over all these years started to formulate different types of charts and arrangements of the periodic table, and gradually led up to what we use today. Ready? One scientist named Robert Boyle, he believed that we could turn one element into another. Theoretically, we would have to change a number of protons in the nucleus. There's an old fairy tale called Rumpelstiltskin, and he was a little troll who could spin straw into gold. Well, straw is made of carbon, only 6 protons. Gold is element 79, so 79 protons. That's adding a lot of protons to the millions and billions and trillions and quadrillions of atoms that make up a bundle of straw. So that really is impossible. Robert Boyle was wrong. We can't easily change one element into another. Now, some elements can be forced in nuclear reactors to become a different element, and that's something we're going to talk about another time. There aren't many who can do that. But Boyle did help discover that each of the elements is very unique. Each atom, each element has its own unique properties, very different than most of the other atoms. Now, there are some pairs and groups of atoms that have somewhat similar characteristics, but many of the atoms are very different from each other. Boyle also helped discover that matter has indivisible particles of elements called atoms. He agreed with John Dalton. We talked about Dalton's 5-part theory earlier, but now we know, though, that one part that says atoms are not divisible, well, we know that that is false now, but Boyle and Dalton agreed at that time. Remember, the word atom means indivisible. Ready? Antoine Lavoisier, probably botched the pronunciation of that name. This scientist discovered that fire needs oxygen to burn. Oxygen is a very flammable gas in pure form. Many people have the fireplaces and they have to put oxygen on the fire in order to keep that fire burning bright. Fire is not an element, but oxygen is. And fire needs oxygen to burn. One way we put out fires is to smother the flames and block the flow of oxygen into those flames. But what about pouring water on the fire? Remember, that oxygen is combined with hydrogen, and when atoms combine, their properties change dramatically. Therefore, the water made of H2O, that's able to put out the fires. By 1779, Lavoisier and some other scientists discovered many more elements. They had to start, as we said earlier, making some kind of a chart, something written in order to keep track of not just the elements, but be able to explain the properties of the elements. It was Antoine Lavoisier who made the first official list of 33 known elements at that time. And again, we now know of 118 elements. This tells me that the periodic table has been formed and reformed over many, many years. It is a workable model, and it wouldn't surprise me if more elements got discovered in the future, but right now we know of 118. Ready? Jacob Berzelius. This scientist devised the chemical symbol system that we know of today. You saw some chemical symbols a little while ago. Gold, AU, copper, CU, and so on. And this started in 1814. Berzelius gave each element a Latin name. Now, we have some names from the English and some names from the Latin, and we'll talk about the chemical symbols where some of them may not look like they make sense, such as potassium. Go ahead and write that up here. Potassium, here's the word, but the symbol is K. Well, potassium is the English name, but K comes from the Latin word for potassium. Gold, you saw this earlier, is Au. Well, the Latin word for gold is aurum. So now that you understand that, you'll see why some of those symbols that look like they don't make sense, now they might make a little bit more sense because they come from the Latin names of the elements. At that time, around 1814, 47 elements were known, and Jacob Berzelius started to give them the chemical symbol. Now, here are the rules that we still use today. If the element has just a single letter for its symbol, that letter is always capitalized. H, hydrogen, N, nitrogen. Now, W means tungsten. The Latin name for tungsten is wolfram, and P is phosphorus. Many of the elements have two letters for their symbols. In that case, the first letter is always capitalized. The second letter is always lowercase. Ag is silver. The Latin word is argentum. Mg, magnesium. That should make sense. Ca, calcium. That should make sense. The reason we want to remember that, you're going to see on the screen in just a little bit anyway, is in compounds, when we see a second capital letter, that immediately tells us we now have a different element. And again, you're going to see that on the screen in just a little bit. Oh, were you ready? The modern element symbols, again, we know of about exactly 118 known elements, and they're ordered by the atomic number. And we've talked about that before. There are 12 elements that use just a single letter, and all the rest of them use two letters. And really, it was in the last few years that the last few elements got their names and their symbols. It used to be something like element number 118 used to be called uninonctium, which is simply the Latin word for the number 118, and the symbol was UUO. But now, those last few elements have their names and their symbols. As I said a few moments ago, in a compound, a new capital letter means we have a new element. So look here. This is glucose, C6H12O6, copper, hydrogen, and oxygen. Since I see three capital letters, I know that this compound contains three different elements. And again, the subscript, the number below, tells us how many atoms of carbon, hydrogen, and oxygen make up one molecule of glucose. This is sodium chloride, capital N, A, capital C, L. Now that can be mixed up as a capital I, but this is big C, little l. So this tells me two capital letters, two different elements in that compound. How many elements are in this compound, magnesium hydroxide? Magnesium, capital O, capital H, oxygen, hydrogen. So this compound has three different elements. That's why we need to make sure that we understand the capital letter and a lowercase letter for two letters in the symbol. When I see another capital letter, I know that's a new element. And that can be important because big C, little o, that's the element cobalt. That is element number 27. It's a magnetic metal, perfectly safe unless you drop a big chunk of it on your pinky toe, and that could hurt. But look here, big C, big O. That's a compound called carbon monoxide, a poisonous, deadly gas that makes no noise and has no odor whatsoever. You need a carbon monoxide detector to tell that that gas is present. And again, that's a very dangerous and even deadly gas. So they're both C and O, but look at the capitalization. Big C, little o, one element. Big C, big O, compound of two elements. Even though the letters are the same, the uppercase, lowercase, that tells us they're two completely different substances. Ready? Now, the development of the periodic table. Let's remind ourselves of a definition here. Periodicity. Repeating a pattern. Just like with our class schedule, we go 1 through 7, and tomorrow we go 1 through 7 with some exceptions, but basically we repeat our class schedule every day. We've talked about that before. Periodicity refers to repeating those patterns of elements as we go from the left to the right. The characteristics and properties vary, then vary some more, then vary some more, then vary some more, and start over when we get to the end on the right side and begin again on the left side on the next row. Remember, a row is called a period. So the repeating patterns of elements suggested listing the elements by the atomic mass, and that was great for a while. However, there are a few places on the periodic table where that didn't work out. In fact, as far as mass goes, argon's mass is a little bit larger than potassium's, but argon is atomic number 18 and potassium is atomic number 19. And as more got learned about the elements, scientists started to realize we'll be better off by putting things in order of atomic number instead of mass number. The pattern showed similarities in the pairs of elements around the 1860s. The pattern repeated after every 8 elements. We started a brand new pattern. We mentioned energy levels last time. A new energy level formed. Now, even though period 3 can go up to 18 electrons and period 4 can go up to 32 electrons, you may remember that from the last session, realize at the outside level, no matter which energy level it is, except for 1, because that stops at 2, when you get to period 2 through period 7, the outside level will never pass 8 valence electrons. And then the patterns repeat when we start a new period. Every 8 elements. Ready? Periodic law refers to that periodicity that we saw on the last page. A scientist named Dmitri Mendeleev, who has an element named after him, Mendelevium. Around 1869, he formed the periodic table that is closest then as what we see today. So he started all this that we see. You look at the periodic tables in your textbook or in the room, you can thank Dmitri Mendeleev for forming the periodic table that we're studying now. Of course, not all the elements had yet been discovered, but he started to notice the patterns and realized the elements that weren't discovered yet, for example, maybe copper, which is 29, had properties similar because of the other periods showing the order of the properties. There must be an element that fits into that space. So he left openings, and as elements got discovered later on, those elements fit into the openings that Mendeleev left behind. Chemical properties are periodic functions. They repeat the pattern. Each atom has a neutral charge. We talked about this last time. For example, the number of protons in a copper atom is 29, is equal to the number of electrons. And a quick reminder, we mentioned copper, so 29 protons and also 29 electrons. That's a total charge of 0. Just add up those integers. So every atom is neutral by itself. Ready? The modern periodic table, Henry Moseley in 1914 discovered the atomic numbers to be the number of protons. And scientists then, because some of the masses were actually out of order, higher, 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 and occasionally drop down, and higher, 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 and again occasionally drop down. So the scientists like Moseley started putting the elements in order of the atomic numbers, the number of protons instead. These elements fit horizontally into the periods very well, in fact, even better than by atomic mass. And you can see more about that on pages 80 to 81 of the textbook. A period is also called a series. That's a row that goes across the periodic table. You'll see a picture of the periodic table again in just a little while. These elements seem to fit better in this order instead of atomic mass. And that turned out that also the elements lined up vertically as well, even better based on their chemical properties. And the columns that go down the periodic table are called groups or families. Remember, we've talked about valence electrons a little bit, and we'll do a lot more with valence electrons. The valence electrons line the atoms up on the chart vertically and show which atoms have pretty similar characteristics. When we talk about chemical bonding before long, that will come into play even more. Ready? All right, here is your periodic table. And as we said, a period goes across. I'll try that again. A period goes across. So this is period 4. And all elements in period 4, do that in case that 4 is hard to see, they all have 4 energy levels. So if you think of a Bohr model, which we mentioned before, All elements in period 4 would have that energy level structure. And then you fill in the electrons 2, 8, 18, 32 up to that. But realize something like calcium right here, that's 2, 8, 8, 2. So 2, 8, 3, 4, 5, 6, 7, 8, 8, and 2. That's your electron structure of calcium. And then to get another electron after krypton, you'd have to start a 5th energy level. And all of these have 5 energy levels, and then the pattern repeats again. Going down a column, let's move that out of the way. All of these elements have 1 valence electron. All these elements have 2 valence electrons. I'll talk more about all these another time, but let's skip on over here to 13, which is also called 3A. All of these have 3 valence electrons. So by ordering by atomic number and learning more about each atom, scientists realized, hey, we can also group them not only horizontally by atomic number, but vertically by the number of valence electrons. Most of these, called transition metals, have 2 valence electrons, but there are some that have only 1 valence electron. Okay, and all these have 4, so that's why it's 4A. All these have 5 valence electrons. All these have 6. All these have 7. Almost tripped. And except for helium, all these have 8 valence electrons. But helium can have only 2 electrons total, has 2 valence electrons, then 8 all the way on down here. So as we learn more and more about the periodic table and we do some practice work with that, that should become a little bit easier to follow. Later on, we'll talk about these 2 bottom rows. That's coming a little bit later, not too far from now. Many periodic tables do have the color codes, as you see here. The group 1 or 1A is called the alkali metals. See the red. This is the alkaline earth metals. You see the orange here. Transition metals in yellow, and so on. Now it's colored differently in the textbook and the ones on the wall. That's okay. At least they have some kind of a color code. And there are other things that may not be shown on here as well that we'll talk about as we get into an upcoming lesson very, very soon. Ready? All right, so ends this set of notes. The next time we'll talk more about groups and families and how elements are classified into the groups and families in more detail than we just said. Thank you for your attention. Good night.